Okay, then shall we start? So welcome to afternoon session. So first speaker is Tillim. She's talking about upcycle symmetry. So please start.
Everyone, thank you so much for coming. So we've already heard quite a bit this week about non-invertible symmetries. And as a reminder, these are ones which, instead of composing in a group-like way, OGOH is the same as OG after H. They instead have a kind of like algebra-like composition. So that's when you allow sums on the right-hand side of different operators. And like with any algebra, you don't in general have multiplicative inverses for these things. They're often called non-invertible symmetries. So I'd like to talk about some efforts to try and make non-invertible symmetries into invertible ones. So one way to get non-invertible symmetries, which is quite typical, is by gauging a theory, say, let's call this theory G, and we gauge it by some subgroup S. G has completely invertible operators, but in general, by gauging S, we will break some elements of G. So if we say, let's call K G without S, and let's also further suppose that SK S inverse is within K. So generically, there'll be some elements of K which are not gauge invariant, and so we might usually think that they are broken, but we can now pass to the group algebra. So we allow ourselves to add elements of the group with a plus, and we can define a new element, TG, as the orbit under all the elements of S of the element G. So this thing, now that we've allowed ourselves to add things to, oh yeah, sorry, go on. My bad, it's very, very sloppy. This is the symmetry group of the original theory. Let's assume it's a zero form. This is just more like an illustrative example of why you might do this. So you can form this new object, which is in the group algebra. And this thing is, well, firstly, it's gauge invariant, because action of S just permutes the items. Secondly, it's a symmetry operator because it commutes to the Hamiltonian. Everything in G originally commuted to the Hamiltonian. This commutes to the Hamiltonian. Great. But the one thing it doesn't have necessarily is an inverse, because it's a sum. It's an element of an algebra. Now let's say we've done this. We've gauged this S, and so we also form gauge invariant states. So say our original states were psi, and let's make gauge invariant states which again are the orbits under our gauge symmetry of the original states. And this guy actually has a nice action on these guys. It's perfectly well defined with a nice charge. So you'd have like TG acting on psi prime, gives you something, just a sum on the outside. Where the original, this is where the CGs are. So that's all fine, there's no problems. However, in general, you'll find that this TG note doesn't have good action on operators in your new theory. Action on states is nice, but on operators is not necessarily so nice. And that'll be quite typical. Okay, so we've defined some new guy that is that's gauge invariant and a symmetry operator, but is not invertible. So let's, without loss of generality, I think I know, assume this to be Hermitian, because you can always form TG plus TG dagger. And so we have a Hermitian gauge invariant symmetry operator, or Hermitian gauge invariant operator which commutes with the Hamiltonian. And when you have that, what we usually think of it as a generator, and we would exponentiate it. We would think of it as like a Lie algebra element, exponentiate it to get some sort of group. So let's try that and formally define. Ooh. That's embarrassing. Beg your pardon, technical difficulties. Oh, you should have pockets. Women's clothes don't really have pockets so much. Okay, so let's formally define our, what we call the upcycled operator. So this guy, he lives in the, well, like in the completion of the universal enveloping algebra of the group algebra. It's just for now a formal definition, but it does actually have a perfectly nice action on states. In fact, either a U1 or an R action on the states. So we, whimsically have called this the upcycled operator, and this is going to be either U1 or R. The thing to do now is give an example or answer a question.
Could you say when it's U1 versus R, because that would like tell us about the charge quantization, right?
It's exactly to do with the charges of the states under TG. So I'd say typically it's R. In very special cases, it would be U1. So we can see that much better in the quantum mechanics example I'm going to do.
Thank you.
Sorry? I can just take TG plus TG dagger and make a Hermitian version. Okay, so example number 1 is the quantum mechanics on a ring. And I'm going to take the case of like no magnetic flux going through the ring, theta equals 0. But this also applies without qualitative difference to theta equals pi. So here we have a Hamiltonian, just p squared on 2m. The eigenstates in the position basis go something like that. There's a U1 symmetry, which I'm gonna call the group element G alpha, and that sends Q to Q plus alpha periodically. And there is also at this value of theta and at theta equals pi a parity symmetry. Sends Q to minus Q. And these don't commute, they form O2 together. Now, because they don't commute, it means that if we choose to gauge P, we break pretty much all the G alphas except for G pi and G0. So gauge P. The invariant states, again, are just the orbit under P. And then we have this, we define our gauge invariant operator, T alpha, which is gauge invariant, and as I just said, and a symmetry operator because G alpha are commute with the Hamiltonian. And then we can see that this is actually non-invertible. If we have T alpha and then some T beta, this is going to give you 1 over square root 2 T of alpha plus beta plus T alpha minus beta. So for a generic alpha, there is no inverse. Now we upcycle. So U alpha of beta, e to the I beta, T alpha on square root 2, just like convenient normalization. And this thing, again, as we've seen before, it has a very nice action on states. So n prime, our new gauge invariant states, is e to the I beta cosine n alpha n prime. So the charge of state n prime is cosine n alpha, which means that for generic alpha, this is going to be R action. There'll be no consistent way to normalize it so that it's a U1 action on all states. There are some exceptions. So one nice example is alpha equals pi over 2. Then you have states with n equals 0 mod 4 have charge 1, 1 mod 4 have charge 0, -1, and 0. And in this case, if we then chose to gauge this one symmetry, then we would just project down onto the onto these states 1 mod 4 and 3 mod 4. But for generic alpha, pi over 3 also works, but most values of alpha will not. There will be an R symmetry. Okay. Example number 2, in slightly higher dimensions, 2D critical Ising, famous non-invertible example. So here we have usual 3 topological lines. So that's the identity eta and n. That's our non-invertible one. And we have 3 genuine local operators, nothing, epsilon, and sigma, I'm going to call them. And then we also have this disorder operator mu, which can only appear at the end of an eta line. So the fusion rules, famously, the relevant one is that you compose n with itself, and these are all like ostensibly self-dual, non-oriented. You get 1 plus eta, and this is the non-invertible part of the theory. So this is the guy we're going to upcycle. And it turns out if you expand this in the power series from before, it actually becomes something kind of neat, which is cosine squared beta on 2 times the identity line minus sine squared beta on 2 times eta plus I on square root 2 sine of beta n. So you firstly point out this is not a simple line, and secondly, it has non-integer coefficients. And I will, in just a moment, I will discuss some of the subtleties associated with that.
Is it, I mean, maybe I just haven't seen it. Like the fact that you're taking like complex coefficient is fine.
Well, I will discuss that. Sometimes it's not fine. But so that'll be I think probably after I've gone through this, we'll talk about that. Okay, so the action of this thing on the states is perfectly nice. On the vacuum, e to the I beta, so that's its quantum dimension, funny. On the epsilon, it's e to the minus I beta times epsilon. And on sigma is uncharged. However, the action on operators is nasty. Of course, it was originally nasty. I mean, n doesn't act nicely on sigma. I mean, sigma isn't an eigenstate of n. So there's some of that business with like trailing eta lines that all comes out. But what's more weird is the action on epsilon, which had perfectly well-defined eigenvalue under n. Now I have un, and I pass it through the epsilon. The epsilon, you can kind of think of as being left alone. Un gets conjugated. So that's funny. And what I think a lot of it boils down to is that since we have a non-simple line, we lose a lot of the stuff that we're used to using, a lot of the topological manipulations and networks. A lot of this is true of any non-simple line. And I believe it's associated with the lack of a local current. So if I have some, going back to a slightly more general example, if I have some element which I write as the exponential of a local current, then if I have G plus G prime, this is going to be cosine. G same alpha. Anyway, it's not going to be, I was thinking of a special case of G alpha. So G alpha plus G minus alpha, like we had before. That's the cosine. That was our T alpha from the quantum mechanics example. And therefore, U alpha of beta is E to the I beta cosine of alpha equals star J. So it is not itself the exponential of the integral local current. This means you can't do things like locally fuse pieces of the same line with itself. And you get this kind of weird behavior. It doesn't really make sense to put networks together, I think. You lose a lot of the power, but this is true of any non-simple line already. It's something to do with the non-integer coefficients.
Am I right to say that, okay, this U defines a perfectly good operator on the Hilbert space once you quantize on a space like slice, but you cannot understand it as a topological defect.
Yes.
Because this weird coefficient that you have, and this is also at the origin of this strange action on operators. Is this true?
Origin of the strange action on operators.
I mean, because when you
Maybe.
look at the action of the on the operators, you are not looking at U as an operator on the Hilbert space, but you are understanding it as a defect in the full space time.
Are you? I never thought of it that way. Is that the case? So that's a correspondence?
No, I mean you have to bend it in that way, no?
Mm-hmm.
The U. So it is not like a line stacked on the Hilbert space. And in that case, it's perfectly fine because you cannot, I mean, you can take arbitrary linear combination of operators on the Hilbert space, and this is fine. But
Yeah.
when you understand it as a topological defect in the bulk, this is not legal.
Yes, this is the big problem. So if you have Euclidean field theory, this is absolutely illegal. There's two roles played by these kind of operators. Firstly, they can be operators acting on a Hilbert space. So let's say we have a time direction. We might think of time going like that. Hilbert space, and you insert your operator on some space like slice, and it just takes states to other states. Now the other role of operators is as defects. And that looks more like this. Kind of time like slice, sort of intersecting your Hilbert spaces, and that will set up a defect Hilbert space on the boundary. Now, having non-integer coefficients in front of these guys apparently will lead to serious inconsistencies and problems like non-integer dimension of defect Hilbert spaces and things. So what we would like is to restrict ourselves to only allow ourselves to think of them as operators on a Hilbert space. Now, in Euclidean field theories, you cannot make this distinction. So you will always be able to, time-like and space-like are obviously interchangeable, but if you think of like, you're starting with some boundary, you think, okay, well, maybe here's my initial Hilbert space and here's my final Hilbert space. And I only allow myself to insert guys in the bulk and she'll be fine. But for Euclidean field theory, you have to be able to cut wherever you like and set up new guys with Hilbert spaces here. I did that. And here. So wherever you put it, there would be some cut which intersected it, and then you would have to consider what the defect Hilbert spaces would be like. So this is probably no way not salvageable. However, for Lorentzian field theories where you have a well-defined time direction, you don't require this kind of cutting and gluing. You're allowed to say, no. Here's the initial Hilbert space. Here's the final Hilbert space. That's where they are. They stay there. And I'm just not going to talk about cutting and gluing. And this is associated again with a kind of lack of locality. That seems to be a sort of running theme. And that's kind of the message I wanted to end on, that there was no local current, but that's true of all non-simple operators anyway. And also that you don't have the locality of kind of cutting and gluing. So perhaps there is some dialectical relationship between unitarity and locality, and who knows, maybe in like a non-local theory, you should be looking for perhaps non-invertibility somewhere, or I'm not sure. And that's a depressing note.
Thank you so much. So is there any comments, questions?
Is there a version of selection rules that these ones would impose on the correlation functions?
That's a very good question. The problem we've been finding is that because operators don't have well-defined behavior, it's sometimes hard to derive selection rules that are not just sort of already trivial. Like in general, the only operators that react well, transform well into these are projectors. And projectors, you've already got very strong selection rules anyway between them, but possibly later.
Anything else? Okay, if not, let's thanks to the speaker again.
Yeah, let me write down something and then.
Oh, okay.
Yeah, just the title. Yeah.
Okay, then let's start. So next speaker is Grigoletto. He's tell us about tubes and representation theory for categorical symmetry.
Okay, thank you very much. Hope you can hear me. So today I'm gonna try to tell you how you can actually define mathematically representation theory for categorical symmetries and how this is related to some categorical constructions, which we're gonna call tube categories. This is based mostly on results presented in this paper, written together with Thomas Barch and Meshi Ballimore. If you want to see other details, there is this prequel paper written with the same people, and these other two papers written by Laksha Bhardwaj and Sakura Shafarnamäki at the same time. And Laksha, I believe, already talked about this on Monday, a nice talk on which I'm gonna try to add. So in order to understand how categorical symmetry acts, it's kind of useful to start from the two-dimensional setup and try to understand what is actually going on from the group-like case first. So as actually already pointed out on Monday for those who were already here, we can think about representation theory for genuine local operators with respect to a group like symmetry as some particular functor. So the situation we have usually is that we have some local operator that is going to be genuine. So we can think about it being attached to some trivial line, and we're going to surround it by some defects supported on S1. And the usual situations that describe the symmetry actions is by shrinking such defect so that eventually we have a new defect, which is going to still be genuine. Description of this geometrical situation is given by the fact that we have to identify a vector space, which is the vector space generated by the operators which get mixed by the action of your symmetry. And then we want to have some linear maps between for this vector space for each element of your symmetry group G. So we can actually translate the notion of a symmetry as a functor which goes from the looping of your symmetry category G into the category of vector spaces. So this means that we start from a category which has just a single object. We want to map this to a particular vector space. And then we have that the various morphism of this category, which is just BG, we call BG, has to be mapped to linear maps, right? This is the standard thing that defines representation theory for local operators, okay? So now we can ask ourselves, what about representation theory for categorical symmetries? And we know very well that for categorical symmetries, the description is much more intricate because the peculiarity of such symmetries is that they can mix operators which lives in different twisted sector spaces. So in particular, we can start from some operator, let me call it O of X, which lives at the end of a line X. And then under the action of some other line B, this may be mapped into some other operator which lives on the twisted sector Y. Okay, so what's going on here? Well, in order to define the notion of a representation, we're gonna have to consider various collection of vector spaces, which needs to be associated to each twisted sector. Okay. And then we're gonna have some linear maps between them that represent the action of a symmetry B and actually the choice of a junction psi between such lines. So we're gonna have to define couples B psi, and we're gonna have some linear maps corresponding sort of actions. So again, as you can see, we have something very similar to what allows us to describe representation theory for genuine operators. But now the difference is that on the domain, we have a different category. So we expect our representations to be described as a functor again into vect, but by starting from some other category, which we call tube category. And we expect the functor, that the representation is described by such a functor. So let me now briefly mention how this is defined. Well, you can just have to look at the picture as nothing particularly deep. We define the objects of this category, the objects themselves of the original symmetry category. Then you define the morphisms in two lines being equivalence classes of such couple B and psi, where the notion of equivalence class comes from the fact that you may have physically equivalent situations where now you may have, for example, that on S1, you're supporting two different lines. And you may collapse the morphism down to the junctions in two different ways. And of course, this has to reproduce some equivalent actions. Okay, besides this detail, what it turns out is that indeed we are able to define such a category. And we we find that the representation theory for these categorical symmetries in 2 dimensions are described by this sort of functors. Okay, so now let me try to answer a question, which is the following. So we know that the symmetry TFT is a very useful tool that allows us to abstract properties of symmetries for any QFT. So we can ask, is there some kind of relations between functors, between the space of functors of these kinds that we are going to call it like? Is there some relation with the symmetry TFT? And the answer is actually yes. And we can view it in the following way. So suppose we are in the same case as before, where now we are introducing our symmetry TFT. Let me suppose that it's a standard 2-0 associated to your fusion category. So we fall in this the case that we have same picture as before, as above. And now we have, in principle, some lines on which our operator O ends on, and which can be extended into the bulk. Gonna be an element in your dream field center, be a coupled U tau, where tau is the braiding. Okay. Well, what we can do is, from the symmetry TFT point of view, we can always take the line that lives on the bulk, we can project it down on the boundary, and eventually we're gonna have a picture in particular, yeah, that we can resolve thanks to the notion of the braiding. And eventually we're gonna find situations like the following, where we just have a new operator, which is the one which you get after the action of the symmetry, defect B, and the line that we projected on the boundary, which can then be promoted back to the bulk, right? So what I just showed you pictorially is precisely a map from the dream field center of your fusion category into the category of functors, so of representations of your categorical symmetry. Okay, and moreover, it turns out that this is precisely an equivalence. So what does it mean? This means that suppose you want to figure out what are the irreducible representation of your categorical symmetry, then you get immediately that, for example, the number of irreducible representation is equal to the number of simple objects that lives in your dream field center. Okay? And this is essentially the descriptions in the 2-dimensional case. So now what I want to show you is that this sort of picture can be extended in the 3-dimensional case, where now you have to worry about both local operators and extended ones. Okay, so let me now go to the 3-dimensional world and let me focus on local operators. And in this case, the pictures are again very similar to what we describe in the 2-dimensional world. In general, we may have local operators, which sits at the end of lines, okay, which we're gonna call like mu. And then we may look at the actions of some codimension 1 topological defect, call it again B. And this might change the twisted sector on which the operator lives. And of course, we're gonna have to resolve the junction here as well. So in this case, we find that's precisely the example as before, with the only difference that now we expect to have morphism of your category to be described by codimension 1 defects and objects to be described by codimension 2 defects. So we can similarly define, in this case, another category, which are gonna label like this. Remind ourselves that the defect is that's acting is supported on S2. And this is gonna be such that the objects are precisely the objects, the one form symmetry that lives in the looping of C. Then the humps are again equivalence classes of couples B and psi. It's nothing new. And then what we get is that, of course, we can associate to any twisted sectors on vector spaces, and then we're gonna have some linear map associated by the action of B and its junctions psi. Oh, that's literally as the case as before. And this means that the representation theory that describe representations of local operators with respect to some categorical symmetry now is again described by functors, which goes from this following, the category I just told you about, into vect. Okay. Now, we have to worry about some other kind of operators, which are extended ones in the three-dimensional world. So in this case, we had to, the picture we have to draw is slightly different, but again, I'm gonna hold all the informations. So we can start from line, let me call it L, which might be twisted, so live in a twisted sector X. And we might wonder that there is an action, wrapping actions with respect to some other defect, let me call it E again, Y. And now the junctions is resolved by some line, okay? But this do not exhaust all the possible interactions that this line may have with topological operators. And this is precisely because now we not only have codimension 1 defects, but we also have codimensions 2 defects. So we might suppose that there are situations where the line has a non-trivial linking with codimensions 2 defects, which I'm gonna label by delta. And of course, there's gonna be some junctions theta. And of course, the codimension 2 defects might be an interface between two different surfaces. Okay, so at this point, we see that we not only we expect to go to one degree higher in the categorical description, simply because we have to take into account about 0 form and 1 form symmetries. And at this point, we can define another tube category, which is very closely related to the other one, where now the objects are the same, and the one morphism are just equivalence classes of B and psi, and the two morphisms are again another couple of equivalence classes. We call delta and theta, where now delta is the one form we are eventually interested in. So we can eventually figure out that indeed, as you might simply guess, that the description of the representation for this kind of extended objects are precisely the functors from T into vect. Okay. And this essentially defines us the representation theory for extended line operators. Now, we may let me give you some example just to fix the ideas. So I want to try to convince you that this kind of formalism can be very useful to start to uncover which properties local operators or extended operators might have in a particular theory, simply because these properties are constrained by consistency conditions of being described in terms of this kind of functors. So, yes.
So, so if you specify the two structure, the representation of local operators or lines,
yes,
of the same symmetry, are they related in some way, or are two completely independent pieces?
They are related. So, for example, you may wonder, okay, let me consider the case where we have two lines and an operator between them. So, what I just told you about right now is that this is a two category. And I just told you about that the object of this two category defines representation of the extended objects, but I haven't told you about anything about the eigenmorphism of this two category. What it turns out is that if you look carefully about this eigenmorphism, for example, in this particular case, let's suppose that you have two lines which lives in two different representations. Let me call it L and K. Okay. You can actually see the topological, sorry, the operators, which in principle might not be topological, between lines that lives in different representations, precisely as natural transformations between the two objects which identify representation in this category. And in particular case, you might take this to be trivial, and then you will find the projective representation of the operators that lives at the end of the lines. So from this particular point of view, it might be more general to start to look at representation of fully extended objects of codimension 1 and start to look at representation as particular cases of lower dimensional extended objects as eigenmorphism of the full eigencategory. But of course, you want to make computations, so you really try to do it degree by degree so that you don't just describe it as some generic map. Okay, so let me try to give you an example. It's going to be very trivial. The point of this brief talk is just to give you an idea that there are such tools that we can use to write down representation, not to give some new physical claim. So we can consider the case in 3 dimensions of a gauge theory with gauge group PO for n. You can call it, if you want, 3D Ising-like. And the categorical symmetry of this gauge theory is given by C being equal, wrap. Okay, not gonna get into the details of this, but for us, it's just important that in this category, the simple elements up to condensations are given by, are just free. And we just have a simple line generating as each1 for symmetry. And then the fusion of these defects are just Ising-like. So we have B squared that generate as each2 from symmetry. Then we have PD, B, have D squared. Yes, 1+. So it's completely fusion-like. At this point, you might start to wonder about the representation theory. And what you can find is that you are eventually able to fully classify the reducible representations in this setup. And you find that there are the number of reducibles are a very particular number, and I'm going to explain later why. There's just 5 of them. And in particular, there are 4 that are one-dimensional, and 1 is two-dimensional. And once you start to figure out all the details in terms of this data, of this irreducible representation, you can make some claims like the following. Suppose you start by an operator O, which is charged under the easy-to symmetry, non-trivially. Then, and which is genuine, then you automatically have, by looking at how these reducible representations are described, that this operator might be transformed non-trivially by the action of the defect V. So if we have the defect V, operator O, then of course get sort of things. Okay, this is something you could have argued probably from some physics arguments, but it's just a way to convince you that something like this, you can figure it out, be completely agnostic about the physics that there is behind the theory, and just by looking at the consistency conditions that classify your irreducible representations. Not just pure. Yes. No, yeah, I'm saying if there exists such an operator, which, I mean, okay, this was a particular example. I'm just saying, suppose that your theory in general has this sort of symmetry. There is such an example. I'm not saying that in this example there is such an operator, but if there is, then it has to lie in the non-trivial representation in general. Okay, so let me quickly conclude by simply telling you how you can get such a statement. Well, what you find is that even in the higher dimensional case, you have important relations between this categorical tube with the description in terms of the symmetry TFT. Again. And by using the same kind of constructions as before, which means you start to think about your symmetry TFT, and you can think about having bulk lines on which ends on your local operators, what you're eventually able to do is to build a map that goes from the center of your category or some other version of it, which I'm gonna write down in a second, and build a correspondence between elements of the dream field center to extended representations and so on. So in particular, in this case, again, you will have, you extend it to the bulk and you will have some surface operator extended to the bulk. What you find is that in these setups, you're able to build a map, in this case from the looping of the dream field center into the category of representations. That's 2. And in this case, from the dream field itself, surprisingly, to the category of representations. The claim is that these are, again, equivalencies. So once we know how many simple objects we have, and we can actually build explicitly this sort of map. So once we have a knowledge of an element in your drift field center, we can understand some irreducible representation both for local and extended operators. And let me conclude by commenting on the fact that, okay, let me focus on the particular example of extended operators, in particular lines, that so far this describe any representations for any kind of lines, be it topological or not. But in particular, we can restrict ourselves to describe the representation associated to lines which are topological, so which in principle generates symmetries themselves. And then what we find is that from this kind of map, we have a natural guess of the the elements which might be associated to the representation associated on which the topological lines may transform. And this can be very useful, for example, to work out whether the lines have an anomaly or not, because it's pretty natural to claim that at this point, we can understand the fact that lines might have a non-trivial representations as being charged under some particular symmetry. So in particular, if the defects lines are charged under themselves, this means that we can treat them as suppose that they are indeed anomalous, that they cannot be gauged consistently. So if you're able to work out from this kind of maps the data that describe representation theory for defects line and potentially also for higher dimensional objects, we can in principle work out whether these generates anomalous or not symmetries. And this is more or less the last remark I can make. Okay.
Thank you so much. Any comments, questions?
All right, can I ask a really naive question? So in the context of ordinary representation theory, it's often fruitful to restrict to unitary representation. So obviously this is being relaxed heavily here.
Yeah.
But is there a generalized notion of unitarity that would, I don't know, apply to some correlators or something like this?
That's a good question. So on the top of my head, I would say no. I have no particular clue. I would guess this might be related to imposing some sort of reflections positivity on the target of your category here. For example, once you restrict yourself to the unitary representations, you just suppose that the is not actually VEC, the category, but vector space is equipped with an emission product. And I guess the same statement could be generalized to go from 2VEC to some unitary version of it. But yes, still no definite statements on that. Yeah.
My one worry with doing that is if you do it the wrong way, then, I mean, you want to say things like U dagger U is not necessarily one.
Yeah.
So what's the right generalization?
Oh, in that sense, well, the defect itself, yeah, do not need to be unitary. I would guess this sort of description I told you about might come in the fact that once you start to think about the defects themselves as to be some DQFTs, and then you might wonder whether you can apply unitary on these DQFTs, which has not, in principle, nothing to do with the operator being unitary itself. You know very well these are not unitary operator in the non-invertible case. Yeah.
So you listed a bunch of like one morphisms and two morphisms. How much leeway do you have in I mean, so is that fully specifying everything, or could there be more? Is there an enriched category beyond the one you're talking about, or?
Well, I've sort of hidden some knowledge about the. I don't know if I understood properly the questions, but once you define this knowledge, once you define your category, in order to make it consistent, you have to define composition as well. And in order to define the compositions, is equivalent to say that you have to have the knowledge to know about how to resolve the possible junctions between defects and so on. And this means eventually that you need to know what's the associator, true associator, pentagonator, and so on of the category. Does that answer your question, or was something else?
It's more in line with like what Francesco was on.
Yeah. Oh, I see. Well, yeah, I mean, one way, so suppose either you know the full category by itself, okay, and then you can just work out what's the representations, or you may be agnostic and say, okay, I just know, for example, diffusion rules. I don't know the fully details about, I don't know, the associator, let's say, then you might try to work out what the generical statements are and see whether some of them are compatible with something that you know, some physics statements that you know, and this might help you. And indeed, I guess, like to try to explain, these are the meaning of these sort of functors are very geometrical. So you already know which kind of situation you have to start to look for to figure out the details. Yeah.
So if we consider 1 plus 1D just for simplicity, and the action of the symmetry on the genuine local operators, in the tube category language, I guess it would be what the representation assigns to endomorphisms of the trivial line, right?
Precisely.
So once we are given that action, we kind of expect that the action on the twisted sector should be almost fixed.
Almost, but sorry, interrupt you.
Yeah, I was just wondering if whether we can the action of extending the action from the genuine sector to the untwisted, twisted sector, whether that can be seen in the tube category language. That
yes. So the point is that in particular in the two-dimensional case, we have a very explicit example. In the description of the genuine-like operators, there is no presence of the anomaly in the description of representation theory, right? You just, for example, from the math point of view, you can see that as the cocycle do not enter in the definition at all. In the tube category, as I said before, instead it's very important because it allows you to define the composition of various defects. In particular, you can, for example, look at the case of Z2 zero-form symmetry in 2 dimensions, okay? And you have, as you may know, let's suppose that you're interested about twisted sectors of this, which is already invertible. So it's already the easiest example you can may look at. And we know that we have this sort of situations, right? That if we start to look at operator which lives in the twisted sector of the non-trivial Z2 line, then these two configurations are equivalent to a plus or minus 1. And this essentially from the tube perspective comes from the fact that we have, once we have two non-trivial Z2 defects and we have a defects like this, then we can always have this sort of conditions, right? Because we can stack the two defects and then we find these sort of things. This is precisely, once you start to look at the details, what tells you that you must have such a relations. And such relations is defined precisely by the value of the anomaly. So in particular, you get that the two things are equivalent if this is non-anomalous. And if this is anomalous. And the way you can see this is that these are actually geometrically equivalent situation, if you want, right? And yeah, and as you know very well, these sort of things, for example, give constraint on the spin selection rule of operators, which lives on the twisted sectors and so on. So you start to see this sort of additional data once you look at the twisted sector, already for the invertible case.
Yeah, thank you.
Thanks.
Yeah, anything else? If not, let's thank to the speaker again.
Fine. I have a question for you later as well. So. Sorry, I'm talking about, for example, yes. Suppose that you have already. Yes. That the association.